Chapter 2, we're going to look at the algebra of functions. In the first cluster, we're looking at addition, subtraction, and multiplication of polynomial functions. So in the first section, we're going to look at polynomial functions. We're going to identify a polynomial expression, identify a polynomial function, and we're going to do the addition and subtraction of polynomial expressions or functions. All right. In this first question, we've got a lot going on here. So we've got a kennel. We're looking to expand facilities. We locate a piece of property. The property has a small building, can't use it, but that's okay. The cost is only $1,000 or $15,000, so we're gonna jump on it. All right. We need a permit to tear down the old structure. The demolition permit is going to be $200, and the building permit is 80 cents per square foot for the new building. So if we let the square footage for the new building be 1,200 or 1,400 or 1,600, etc., we can calculate the cost of the permit. So we've got to pay the $200 plus 80 cents times each of these. So if you take 200 plus 80 cents times 1,200, that should give you hold on, there we go, and move my screen out of the way so I can see my numbers. So it should give me 1,160. So 200 plus 80 cents times 1,200 feet. And the same thing for the 1,400. That would give us $1,320, or for 1,600 square feet, that would give us 14,080, or 1,800 would give me 1,640. So what we're doing here to compute the cost of the permit is we're taking the $200 plus the 80 cents times the square footage. All right. Next, we learn that our construction costs will average about $35 per square foot. We're going to get some donated equipment, so we don't have to pay for that. We just need to pay for the construction costs. So if I take $35 times my $1,200, that gives me $42,000 for the construction costs. If we take our $35 again times 1,400 square feet, that gives us $49,000 for the construction costs. $35 times 1,600 gives us $56,000. And for the last one, $63,000. And so for each of these, our C of X function that we're doing, we're taking $35 per square foot times the square footage, so times X. All right, now we're going to put these together on the next page. And we know that the cost of the land is $15,000, and I'm going to have to pay for that, in addition to the cost of the permit. So I'm going to fill these back in. The cost of our permits, we said $1,160, $1,320, $1,480, or $1,640, depending on how large we decide to make the kennel. Our construction costs were $42,000, $49,000, $56,000, or $63,000. And now we want to know the total cost of the kennel. So the total cost of the kennel, we're going to add up our price of the land plus the cost of the permits plus the construction cost to get the total cost here for each of these kennels, depending on how large it is. All right. In the first one, 15,000 plus 1,160 plus 42,000 gives us 58,160. If I add up the next set, I'm not adding on the X, of course, just the output values here. So that gives me 65,320. 15,000 plus 1,480 plus 56,000 gives me 72,480. And the last one, if I add those up, I should get 79,640. What is the relationship among the price of the land, the cost of the permits, the construction cost, and the total cost of the kennel? So the total cost, the t of x function, it's 15,000 plus our p of x function plus our c of x function. And since I know what each of those functions is, I can simplify this function over here. So I'm going to write down on the side. I just don't have enough room to get it simplified. If I don't use the margin right here. So I've got my 15,000 plus p of x. P of x, remember, was 200 plus 0.8x plus, and then our c of x function, and that was 35x. So if I put all of those pieces together and combine our like terms, we'll get our simplified total function. So our total cost function is 1,000 or 15,200, sorry, adding 15,000 to 200, 50,200 plus 35.8x. So that is the sum function. Sorry, I got to move my screen back over. That's our sum function when we combine our like terms. All right. So let me, again, take my table over here. I'm not going to fill this table. Well, actually, they have different input values. I'm going to fill this one in a second in Desmos. So I'm going to move my Desmos graph over. And what I have so far is I've wrote my p of x function. I wrote my c of x function. And you can see I have the original inputs and the original two columns of the table. I don't have the t of x column right here. But what I want to do is say that what I would like is to add up each of these. The 1500s, I just left the default name y1 for that list. So I'm going to add the y1s plus I'm going to add p of x1. I'm going to add the next column, p of x1 plus I'm going to add c of x1. Okay. And so these should be the totals of the results of the first column plus the results of the second column plus the results of the third column as I put each of their headers into this sum. Pretty cool. And then the new t of x function that we just got was 15,200 plus 35.8x. So I'm going to put one more column over here to evaluate the t of x1 function, just to confirm that we're getting the same thing from our simplified version of the sum function as we did from the literal version of the sum function where we just said add the first column, the second column, and the third column as directions in the table. So they're the same, and it's just kind of interesting to note that you can type it in this way. So you can type the sum in without actually combining the like terms, and then you can make sure that when you did combine them that your solution is correct. All right. So we need to fill out a table similar to this with the new input values. So I'm just going to go ahead and change these input values here to 1250, 1500, 1725, and 2050. So I'm going to write in my p of x values for this one. We would have 1200, 1400. I'm going just down the p of x column right here. 1580, 1840, and our c of x would be 43,750, and so on. I will pause. You can write those numbers down as I continue. And again, just to confirm, I gotta make this a little bit bigger. I can confirm that my sum function and my total function are giving me the same outputs. All right, so let me slide off my Desmos window, and we got our values written in here to the table. All right. Now, that was an addition, a sum of functions. Next, we're going to look at a difference or a subtraction of functions. So let's look at our new situation. The kennel's been built. We're back in business. The kennel can accommodate at most 25 dogs. Your current charge is $35 per day for a dog. And utility bills are $15 per day. Cost of feeding a dog is approximately $15.15 per day. So in the first part, suppose D is the number of dogs in a given day. Determine an equation that expresses the total revenue as a function of the number of dogs on a given day. Okay, so for revenue, we are making $35 per day. That's what we're charging. The other two numbers that we were given up here are bills. So we have a bill we have to pay that's $15 per day. And then we have to feed those dogs. So that's something we have to pay for. We're not getting money for that. So these two are costs incurred. And then this is our revenue. So only the first one is the revenue. $35 per day. And um, if I have 0 dogs, I have 0 revenue. I'm just going to write my revenue function over here to the side. R of D should be 35D, and then we can fill in these values. So 5 dogs times $35 is 175. 10 is 350. 525, 700, and 875. All right, now for our costs. Okay, we have to pay $15 per day. Remember that our input is the number of dogs, so we're assuming this is the revenue for one day and the cost for one day. So $15 is going to be static. It's just going to happen once per day. But then the cost of feeding, this is going to be per dog, right? $15 is per day, but I have to pay $15 per day per dog. And so that's where my variable is going to come in. So my cost function, it's going to cost us $15 per day plus $15.15 per dog. So I have an initial value and I have a variable. So I have my slope right here, the 1515, because it's per dog. So I have my rate of change here. All right, so if I have 0 dogs, my costs that I will incur are $15 because I still have to pay for the utilities. 5 dogs, 15.5 times 5 plus 15, that's going to give me 90.75. And then 10 dogs, 166.5 or 0.50. 15 dogs, 242.25. 20 dogs, $318, and 25 dogs, $393.75. All right. Now we're going to put this together and we're going to compute the profit that we make, which is computed by the revenue minus the cost. We take the revenue function minus the cost function. So I'm going to fill in this by my table first, and then I'll go back and write the equation and we'll compare. All right, so I've already slid this over here. I've got my decimals with my R and my C functions. As you can see, they're filled in. And I would like to do the revenue function. Oops, that was supposed to be a parenthesis. Minus the cost function. And I'm using the table 2. So I have x2s inside here because I still have up above the other table with my building costs and so on. So I have second table with x2s as input, so I use r of x2. I also had to call this little c instead of capital C because I had a capital C function up above, and I can't have two functions with the same name or I won't be able to evaluate them. So I made a little difference and used a lowercase c for my cost function down there. Okay, so as expected, if our revenue is 0 and so no dogs came in and we still had to pay for utilities, our profit would be negative $15. So we have a loss of $15 in that first spot. If 5 dogs come in, we make $84.25. If 10 dogs come in, we make $183.50. 15 dogs come in, $282.75. 20 dogs, $382, and 25 dogs, $481.25. Okay, so we want to write the function. I'm going to just slide decimals off for a moment. To write the profit function, our P of X function is going to be our revenue function, which is 35D, minus the cost function. I'm going to put the cost function in parentheses, 15 plus 15.15D. Hopefully it's not too weird that I have it on 2 different lines here. But this negative, when I'm subtracting off the cost function, does need to be distributed through the parentheses to both parts. So I'm going to try to sneak this in here. So I would have my 35D minus 15 minus 15.15D. And then I'm going to combine my like terms. So our simplified profit function, 35D minus 15.15 this is our profit function. I'm going to call it little p here. And I need to figure out what I say, 35 minus 15.15. So that's 19.85D minus 15. All right. And we're just going to check our solution over here with that table. So when we computed the difference, we just used the difference function. And now if I think I might have used capital P up here. So I got to use little p for profit. P of D is going to be, I forgot, 19.85 D plus, minus 15. There we go. So if I put my P function over here, little p with an input of x2, we should confirm that what our simplified profit function is doing, that difference, that simplified difference, is the same thing as the literal difference, where I told Desmos to subtract the two columns without me telling it what the simplified function was. So all my values should be matching up here. Looks good. Okay. Noting again that when I'm subtracting the function, I should have written this further over the margin. I was trying to squeeze it in, but this negative does need to distribute through the entirety of the cost function. So both 15 and 15.15D became negative, and then I combined like terms from there. All right, so this is our difference function. And over to the next page, we want to sketch the graphs of the revenue function, the cost function, and the profit function on the axes. So that's one of the nice things about putting them into Desmos. I can zoom fit on this table. I'm going to turn off some of the other stuff from earlier just because one of them was showing up. There we go. And I'm going to shrink this over so I don't need to see the table right now, and I can get a better look at this graph and what's going on here. I'm also going to color code these or line code these. So my revenue, let's go ahead and make the dash, the little dotted line, the cost, and the profit, the dash, so we can see which one's which. Okay, so we have our revenue, that's the highest one, and when we subtracted off the costs, we ended up somewhere in the middle, and that's our profit. So the profit is the dashed one in the middle. The revenue on top, now if you imagine this, for each of these values, I had to subtract the 525 minus the 242, and that left me with the 282. So I had to go down by this much, and that put me down here. So we have dropped down by the amount of the cost function to get to the profit function. All right. There's a note at the bottom that since this is the number of dogs for this one, and it's common to draw the graphs with continuous lines like this to see the pattern, these are discrete functions because you're not going to have half a dog come into the kennel. So they're discrete functions. They have more inputs than just the dots. So if I turn this off and just look at the dots, that would be a little misleading. It's not just those dots because this is just 5, 10, 15, 20. And you could have one dog or two dogs or so on. So we look at them with the lines, though technically this function is discrete and they should not really be connected. Just a note right here. It's just a common caveat that we're going to put on this graph that they're not really connected. All right, so I'm not going to draw on my page, but if you want to make a quick sketch, you can. And then part B, it says use the graph to determine the break-even point for the kennel. So that is the place where the profit is equal to 0. So I'm going to look at just the profit function for a second, and I want to find out when the profit is equal to 0. So if I click on this, if we have 0.756 of a dog entering the kennel, our profit would be 0. So obviously we can't have 0.756 of a dog. So what this means is that if even one dog comes into the kennel, we'll make a profit. So that's a pretty good business model. If they have 0 dogs, there's a loss. But if even one dog comes into the kennel for the day, the kennel makes a profit. So their business is going to be successful. All right, so I'm going to make some notes about that over on the side. So the break-even point is, it was 0.7 something. I forgot the number. 56, comma 0. So if even one dog comes into the kennel, they make a profit. Write and solve an equation to determine the break-even point. Okay, so there's 2 ways to write this equation. I can write that the profit function has to equal 0, break even when the profit is equal to 0, or I can write that the revenue function has to equal the cost function, because when the revenue equals the cost, they break even. Now, these 2 things really are the same. I guess I should put D as the independent variable since I use D for the number of dogs here. They're the same because remember that P of D is equal to R minus C of D. If you add the C to the other side, you get R equals C. Same thing. So we'll start with this revenue equals cost version. So this would be 35D equals 15 plus 15.15D, and we'll subtract the 15.15 over to the other side. That should give us our 19.85D equals 15. And then we'll divide both sides by 19.85. So that should give you D equals 0.756. And that will be the number of dogs required to break even. We'll round it to a whole dog so that we know that we're going to break even actually below 1 dog. So by 1 dog, they've already made profit. Now, it's not enough to just make profit, but now we want to have a profit of at least $150. So how many dogs must we have? Okay, that's an output value. So in our graph, we're going to want to just graph y equals that output value, y equals 150, and we'll find out that we make a profit of at least $150 if we have 8.3 dogs. So my intersection point is 8.321, 150. When I intersect this with y equals 150, we move the decimals back out of the way. I just drew a little sketch right there with my ordered pair. So in terms of dogs, I can't make 8.32 dogs come in. And if I have only 8 dogs, I don't make 150. I'm still below 150. So we're gonna need 9 dogs because 8 dogs won't do it. So if at least 9 dogs come in, at least 9 dogs come in, the profit is over 150. And again, just because, I mean, it does round down to 8, but if you plug 8 into the function, you're going to be below 150. You don't get to 150 until you reach 8.3, and whole numbers have to be used in this situation since it is discrete. So it's got to have 9 dogs to get, it'll be above 150, but it will be at least 150. All right. Moving on to polynomial expressions, functions, and terminology. Polynomial expression is formed by adding or subtracting one or more terms of the form a times x to the n, where a is a real number and n is a non-negative integer. So you want your powers to be whole numbers, integers, and you want them to be non-negatives. They must be positive whole numbers. Okay, a can be anything. A is just a coefficient. It can be anything. And those are polynomial expressions. So we can see in the example that there's a couple different polynomial expressions here. 10's a polynomial expression, or 5x, that's a polynomial expression. Or you could have some that have multiple terms, like negative 3x plus 2, and 4x to the third plus 7x squared minus 3, or 5/3 x to the fourth. Those are all polynomial expressions. These ones are not, and the reason that these are not is because the x is in the denominator, no good. The square root symbol, no good. And again, a denominator right here. Those are the reasons that these ones are not polynomial expressions. They do not have just a product, right? A product of a times x to the n. They have some divisions, they have some square roots, they have some things that are not allowed. All right, we want our polynomial expressions written in descending order. So descending order means that the highest power is first. So power 3, power 2. This one doesn't have a power 1, so it skips to power 0. They could be written in ascending order, but that's not traditional. We would like to see things usually in descending order if we're asked to order them, because it's easiest to identify what the leading term is and what the degree of the polynomial is. Definitions towards the bottom of the page. We have monomial. A polynomial is a monomial if it's just a single term. A polynomial is a binomial if it has 2 terms, and a polynomial is a trinomial if it has 3 terms. There's examples here of 3 different monomials, 2 different binomials, and 2 different trinomials. All right. Oh, so write yes if the expression is a polynomial, write no if the expression is not. This is a polynomial because I have whole number exponents and no divisions. This is a polynomial. Yes, because I do have a division, but it's by a number, not by a variable. The variable is not being divided by, so that's fine. Oh, this one is not, and that's because the variable is in the denominator. Can't divide by my variable. This one is a polynomial because I have whole number powers. This one is not a polynomial because of that square root symbol. So I can add, I can multiply, I can divide by numbers, can't divide by the letters. All right. So write yes if the equation defines a polynomial function. If this half of it's a polynomial, then yes. If not, then no. So yes, that's a polynomial. Yep, that's a polynomial. Oh, got an x in the bottom. Nope. Got a square root. Nope. All right. Adding and subtracting polynomial expressions is all about like terms. It's all about combining like terms. Add the squared terms with the squared terms, and so on. The linear terms to the linear terms, the quadratic terms to the quadratic terms, and the constant terms to the constant terms. All right, so that one was an example. We're going to look at an exercise over here. Given the polynomial function, add the 2, subtract the 2, and do some multiplication. Okay, I'm going to try to write really small here so I can fit these in. G of x plus h of x. That wants me to add up the g of x function and the h of x function. So the g of x function is 4x squared minus 3x plus 10. And I need to add this. I'm going to put the g of x function here in parentheses. I need to add this to the h of x function. And the h of x function is negative 3x squared plus 5x minus 2. So because I'm adding, an addition symbol multiplied into a parentheses isn't going to change any signs. So I really can ignore the parentheses for addition only. And I don't have room to rewrite, so I'm going to ignore them. And I'm going to say the 4x squared plus the negative 3x squared gives me 1x squared. The negative 3x plus the 5x gives me 2x. And the 10 plus the negative 2 gives me 8. All right, so this is going to get compact real soon, so I'm going to draw a line to separate this one from the next one. All right, so next, this one's the subtraction. So in the subtraction, again, I start with g of x, because that's the one that's written first here. So 4x squared minus 3x plus 10, this time minus h of x, which is negative 3x squared plus 5x minus 2. This time, because of the subtraction, I can't just ignore the parentheses because this negative does need to be distributed through. So I'm going to rewrite underneath this one without the parentheses. So this is equal to 4x squared minus 3x plus 10, no change in the first, but in the second one, this negative times the negative 3 will make that a positive 3x squared. Negative times a positive is a negative 5x. Negative times a negative is a positive 2, and then equals 4x squared plus 3x squared is 7x squared. Negative 3x minus 5x, that's going to be negative 8x, combining our like terms, and then the 10 and the 2 is going to be plus 12. So our answers, again, I'll just kind of circle the answers here at the end for the addition and for the subtraction. Okay. All right, and then I'm going to underline there to say that one's now finished, and we're going to go to the last one, which is our product. This is negative 2 times the g of x function. So negative 2 times g of x, so that's 4x squared minus 3x plus 10. And again, that negative 2 is going to distribute into all three terms. This is a trinomial. It has three terms. Terms are separated by the plus and the minus. So negative 2 times 4 is negative 8x squared. Negative 2 times negative 3 is positive 6x. And negative 2 times 10 is negative 20. And so I don't have any combining of like terms to do here because I don't have any same term, same powers. I have a single x squared term, a single x term, and a single constant term. So I just needed to finish the distribute.